Jacopo Bassi from IMPA, and the title is on some weak version of hyperbolicity.
So thank you very much for the invitation. It's a pleasure for me to give this talk here. And thanks everyone who decided to attend this talk. Yeah, the topic of the talk is really about some, as you see, some weak versions of hyperbolicity, in particular from the analytic point of view. And so first of all, I want to start by recalling some topics, basic topics in analytic group theory, since it's always good to remind some notion and some results that will be important, at least as motivating results, and also to fix the notation. So first of all, let me tell what is very loosely speaking analytic group theory. Analytic group theory is basically the study of properties of groups, so invariance and stuff like this, from the point of view of unitary group representations. So this is something that was started by, I think, Harish Chandra, and in this talk we are actually interested in groups which are discrete. And now I will always talk about representations, by meaning that they are unitary group representations in this talk. Unitary group representation means that it is a homomorphism, continuous homomorphism from the group to the unitary group of a Hilbert space. Now, an important tool in order to study this are what are called operator algebras. So first of all, or a language, if you want. First of all, I will remind how to construct operator algebras given a group. So let me briefly recall what are the group algebras. So in some sense, we want to construct some operator algebras, so algebras of operators on a Hilbert space. We should detect properties of the group. So the easiest way to do so is the following. We start with an algebra. So just as a set, this is basically the finitely supported functions on the group. And now we want to give to it the structure of an involutive algebra. So since we want to recover properties of the groups, the basic idea is to tell, okay, I take two of these, for example, the delta function on a group element. I want to multiply this with the delta function on another group element, and now I declare that this is just delta of the product of the two group elements. In this way, at least I have the group structure already in this algebra. And now there is also an involution. The involution is basically what is taking the adjoint in the bounded operators on a Hilbert space. And the involution, I declare that it should be something like this. The star of delta gamma is delta gamma to the minus 1. At this level, what I obtain is an involutive algebra over the complex numbers, and I would like to complete in order to obtain what is called the C-star algebra. Now there is a standard procedure to do so, and the procedure is the following. Suppose we have a unitary group representation from gamma to the unitary group of a Hilbert space, then automatically it's easy to check that this induces an involutive algebra representation. So this gives a representation of this involutive algebra into B of H, where H is the same. So we can complete the image of this inside B of H, and we obtain a C-star algebra. The closure ring norm, for example. And we obtain a C-star algebra. So at least in order to be able to use should know that there are at least some unitary group representations. Now, in the discrete case, indeed, there are several. In general, it's not true. If you have a group which is not locally compact, it's very difficult to find a unitary group representation. But since you are only interested, I will always consider gamma that is discrete and also countable in this story. So let's see if we can make a list of unitary group representations for a general group. So certainly we have the trivial representation from gamma to the trivial group, and this will give a system algebra that is trivial, but at least this is a representation. So this is the trivial representation. Now, I can also construct what is called the left regular and the right regular representation, because the group is discrete, or in general, if it's locally compact, you have one measure. This is the point. They are denoted by lambda, rho. So lambda is the left regular, and rho is the right regular. The Hilbert space is the space of L2 functions, in this case with the counting measure. And I say that lambda gamma applied to an element psi, where psi is of course in L2 of gamma, evaluated in eta is psi gamma to the minus 1 eta, and similarly for the right representation. Rho gamma psi evaluated in eta is psi of eta gamma. And we can complete inside this. The completion will give us what is called the reduced group system algebra.
I'm already starting to be lost. Because I have nothing. I know nothing about these things.
So
it's slower, and what is written here? Lambda.
So I take, I want to define a group representation from gamma from the unitary group on a certain Hilbert space.
Yeah.
Now I say that the Hilbert space is L2 of gamma. The L2 functions.
L2.
Yeah.
Because it is smaller.
Yes. And this is just translation. I take my L2 function, I translate here from the left, and for the right regular from the right. And the gamma to the minus 1 or gamma are just because I want to have a group representation, just to be sure that this is really a homomorphism groups. So I take this, as I said, from a group representation I obtain a representation of this involutive algebra, a representation really of an algebra. And I complete in the norm of this particular Hilbert space. What I obtain in the left regular case is what is called the reduced group system algebra. It's just a name. And is denoted like this. And I also have, for the right regular representation, an analog system.
What happens if you try to do this for a group which is not locally compact? What fails?
The problem is that you don't have the hard measure. So you cannot define this.
And there is no measure. I mean,
maybe you have some two. If you have, locally compact is equivalent to the fact that you have hard measure. And so, if you don't have hard measure, you don't know exactly what to do in order to have a continuous group representation. So this is the main problem. Okay, there are some. Okay, in some cases you have some representations that you know, but okay, I don't want to go into much details here. I will always consider discrete countable in this case. Okay, and this is another example of unitary group representation. So we are building a list in order to be sure that we are doing something sensitive of the group. And another example that is important for my talk is if we take gamma. Suppose we have an action of gamma on a space that is compact and Hausdorff. Now, in general, if I have an invariant measure, I can take a L2 of this measure, and left translation is just it's a unit, it's implemented by a unit. In general, I will not have an invariant measure, but I can have mu that is called quasi-invariant. Quasi-invariant means that if I take, I translate this measure by an element gamma, where the translate is the following. In order to understand what it is, I evaluate on continuous functions. And this is just the integral of this function composition gamma. So this is the notion of translated. And the quasi-invariant means that if I look at the class of this is the same as the class of B. So equivalently, a Borel set has measure 0 if and only if under the translation of every group element the measure is still 0. In this case, I can also obtain a unitary group representation. And in this case, this is called the Koopman representation. And I say that pi of mu of gamma evaluated against psi, where psi now is in L2 of this measure, almost everywhere evaluated in point x, is the Radon-Nikodym derivative of delta gamma mu in the mu, evaluated in x, times the translation. And this gives actually a unitary group representation. So, okay, at this point we have at least some unitary group representations to work with. And
this, because I look at the I didn't understand why here psi is taken from the past and the derivative, this Radon derivative, is about going forward. Gamma, and here gamma minus 1. Something different. Because
it might be the case that
yeah,
in method probably there will be many of these. It could be that this is gamma to the minus 1.
Because for Perron-Froben you take both from the past.
Yeah, it might be that you are right.
Something strange looking in both directions.
Yeah, I should write I mean, this is something one should check if there is gamma or gamma to the minus 1. Yeah, probably you are right.
No, I don't know.
But I don't know. Okay.
Why square root?
Because in this case you obtain a unitary group representation. You want that this is a unitary. And so this is just because of this. If the measure is invariant, you don't need this. If this is quasi-invariant, you have to cook around this Radon-Nikodym derivative.
And my intuition Perron-Froben is not good because you are considering Koopman.
Yeah.
Not Perron-Froben.
Yeah. And okay, so now we know that we have some unitary group representations, and we can do also something a bit abstract. We take a family tau of unitary group representations, and we construct a sister algebra using this family. So in this way, we take an element on C of gamma, and we declare that the norm of this element is the sum over all this family of representations of the norm of pi over. We complete, and we obtain a sister algebra that we denote in this way. And okay, so in particular,
So f is just function on gamma, yes? Complex value.
finitely supported function on gamma.
Finitely supported.
Exactly. With this algebra extraction. This is an algebra, an evolutive algebra. And we can take a family of representations and obtain again a sister algebra. Sometimes these are called exotic group sister algebras. Okay. And for example, if we take tau that is the collection of all the unitary group representations, so tau is equal to really all the unitary group representations, what we obtain is called the full group sister algebra. Now I will use this terminology. For me, a family of group representations is called the existar topology, just on the group. And they say that the group representation pi is tau continuous if we have the following, that whenever I take, so from the definition, it's easy to see that if I have this type of completions, there are always quotients of the full group system algebra, because I'm restricting to some representations. And I say that the representation is tau continuous if it factors, sorry, this is star of pi, factors through this particular condition. This is just a terminology. In particular, in the language of Harish-Chandra, pi is lambda continuous, where lambda, I recall, is the left regular representation. If in this case it's called the template. So it's an element of the template duality. So this is just some notation. And okay, now I want to discuss a little bit about amenability. And the reason is that this will be motivating for what I will say later. So I will start just with the definition. The concept of amenability really comes from the Banach-Tarski paradox, and it's really the group theoretic content of the proof of the Banach-Tarski paradox. The Banach-Tarski paradox is basically the fact that if you take rotations in 3 dimensions with the discrete topology, it's not an amenable group. And this is not the case in 2 dimensions. This is really the point. So, for me, a group gamma is amenable.
So, do you have this measure or no, it is without measure? Because it's sometimes.
Where, sorry?
It is L2, so no, this is.
In this case, I take the counting measure.
Yeah, and
because I have a discrete group.
I see, and here you have this group, this measure, or you don't?
Yeah, I want only to consider discrete groups, but of course the concept of amenability is well defined also for non-locally compact groups, actually. So it's
no, but here you will not use any measure, won't you?
No, here I want to say a property of the group.
Of the group.
Of the group, yes. And I say that gamma is amenable if we have the following, that there exists a mu that is a probability measure of the group, but it's only finitely additive. It's not countably additive. So yeah, now I have a measure. Finitely additive and left invariant. So let's call it lambda invariant, probability measure. And then using some, so equivalently, using some approximations, this is equivalent to the fact that there is a sequence, since my group is countable, of, let's call it mu n, of probability measures on the group, such that the following holds, that for every gamma in the group, if I look at the translation of the measure by the element gamma minus mu n, I look at the norm 1, this goes to 0. So now we have a notion of amenability that was inspired by this strange phenomenon that is the Banach-Tarski paradox. And okay, let's see if there are groups which are amenable or groups which are not amenable. So let's see some example. The first example is, of course, if we take the integers, and in this case it's easy to check this condition. This condition, so what is a probability measure on the group? It's an L1 function for the counting measure. And in this case, we can take mu n, that is just the characteristic function of the ball of radius n, cardinality. One can check that this is actually, these are called approximately invariant means. This is actually such an object. And also we can use some result that amenability is stable under semi-direct products. And is stable under taking subgroups. So from the first, the fact that it's stable under semi-direct product, we immediately obtain that, for example, in SL and Z, the group given by 1 on the upper triangular group, 1 on the diagonal, here something, and here 0 is amenable. And okay, now we have examples of amenable groups, and let's see if we have also examples of groups which are not amenable. And the standard example is the free group on two generators. So if we take gamma, the free group on two generators, it's very easy to see. How should we see it? Well, this is called the Kelly graph of the group. It's constructed in the following way. We put here the identity. This is a trick. Put here the identity, here the element A to the minus 1, B to the minus 1, and so on. For example, here we have A, B, and so on, and we construct in this way all the possible group elements. Now, suppose that we have a measure that is finitely additive, as in that case. So let mu be like that, and so we do the following. We divide this into some sets. I call this S of B, S of A, and so on. So S of B is just the words, the reduced words, which begin with the letter B. And S of A is similar. But now you see, suppose that S of B has measure that is greater than 0. Then also the measure of B to the minus 1, S of B, is greater than 0. And it's the same actually. But now if we apply B to the minus 1, we obtain all the words except the words which start with B to the minus 1. Because this is a rule when I construct words starting with B. But so this contains, so this is just S of B union S of B to S of A union S of A to the minus 1 and also the identity. But now this means that S of A and S of A to the minus 1 is measured 0. But then I do the same. So mu of S of A is 0. But then I do the following. I apply A to the minus 1 to this set, and this will contain S of B. And so S of B should have measured 0. And this is impossible. So the free group on two generators is not amenable, and in particular every group which contains a free group on two generators cannot be amenable. So in this case we see a plethora of examples. And why did I talk about amenability? Because there is this
very similar to the proof of Orange and Weiss. They have this very similar argument to show that you can, if you would have had the entropy concept for the free group, then you cannot have the property that entropy always decreases. Very similar.
I didn't know.
Yes, I think this was before. Probably they were.
Yeah, probably, yeah. I didn't know.
And yes.
So okay, so amenability is interesting because the following. So gamma is amenable if and only if. Let's say like this. The following are equivalent. So gamma amenable. The trivial representation is weakly contained in the left regular. I don't want to say explicitly what it means, but it's a weakening of the concept of containing. And the reduced group sister algebra is nuclear, and this means that in some sense it can be approximated in a certain sense by finite dimensional algebras is the fact that if we take, now this is star algebra that is a subalgebra of a certain V of H, we can complete with respect to the weak topology, and this is another C-star algebra that is actually a von Neumann algebra, and is called the von Neumann algebra of the group. It's equivalent to the fact that this is injective, that is again some sort of approximation by finite dimensional algebras. And if you want, it's also equivalent to the fact that the full group C-star algebra and the reduced group C-star algebra are isomorphic. So this is, and also something else, that is whenever we take gamma acting on X, that is an action by affine homeomorphism. X is compact convex inside a locally convex topological space, then there is a fixed point. So this is to say that we have different characterizations. One with dynamical properties, other two that are really about the structure of operator algebras associated to group, and if you want, also the fact that we have unitary group representations.
Can you explain? I cannot read the first line, and I don't understand the second and the third. What is the first line? T?
Gamma amenable.
Gamma amenable, and then the next.
The next one is that the trivial representation tau is weakly contained in the left regular. So I didn't define what is weak containment,
okay.
but it's a weakening notion of containment. It means that if you look at the matrix coefficients, so the matrix coefficients are the following. You take a vector in your Hilbert space, and you apply group elements. And this is a map from, is the following. Gamma to scalar product, gamma psi, psi. And this is a map from the group to the complex numbers. Now if you look at this map in the smaller representation, you can approximate this map by matrix coefficients coming from the bigger representation. This is really what it means.
And the nuclearity, what does that mean?
Nuclearity means that you can approximate your C-star algebra by finite dimensional C-star algebras in a certain way, by using UCP maps. It's something about the operator algebra, but it's an important concept in the view. Okay, but this was to tell you that we have, at least in this case, a characterization that is dynamical, a characterization that is really about the structure of operator algebras, and we have unitary groups representation. So it's now a topic in analytic group theory to find properties of groups which can be described from these different perspectives. Maybe from dynamical systems, or from the structure of the C-star algebra, and so on. And some important examples, I will give just two of them. For example, there is a theorem by Osawa that the fact that, okay, I will not define what it is, but this C-star algebra is exact, which means that again you can approximate by finite dimensional C-star algebras, but in another weaker sense, much weaker. Is equivalent to the fact that the action of gamma on its Stonechek boundary is topologically amenable. I didn't define topological amenability, but it's okay. It's the following that. So if you act on a space X, compact Hausdorff, then this action is topologically amenable if there exists a net of maps from X to the probability measures, which are continuous, and such that for every element in gamma, gamma mu in X minus mu of gamma X goes to 0 with respect to the net, and we have to get rid of X, so we take this. generalization of amenability. A group is amenable if the action on the trivial, or on just point, one point, the trivial action, if this action is amenable. And this is a more general concept that is useful in the theory, but okay, just for example, this is an application of this concept. And another example is the fact that the reduced system algebra is simple, so has no ideals, if and only if the action of gamma on its Fussenberg bundle is amenable. Okay, just to give you two examples of this situation in which we have a property which can be described from different point of views. And now I will define what is my dream of desire. Did I erase? No. Okay, this is good. So now I want to look again at the free group on two generators, and this was an argument by Osawa of 20 years ago. So look at this group, and now we take a particular compactification of the group that is called the visual bundle. What is the visual bundle? As a set, is the set of all infinite words, so the all infinite paths in this tree. And the topology is the topology by declaring that an open set is the set of all the infinite words starting with a particular reduced word. And this gives a... Sorry?
It's not Stone-Check?
No, this is the visual bundle. The Stone-Check compactification is not separable. And in this case, you obtain a Cantor set. This is the right thing. And the second time.
What is the name you call it?
Visual bundle. I don't know why visual.
This one?
Visual. I don't know.
Visual.
Why. Yeah, visual bundle.
Visual.
I don't know why. So we take this, and now this has some particular properties. One property that was proved, I think, by Adams, is that the fact the left action extends to an action on this that is amenable in that sense. And another important property is the fact that now consider the right action, not the left. You see that if you take a sequence converging to a point on the boundary, so it's a sequence of words in which the length grows, and if you translate on the right translation becomes negligible at infinity. And this means that the right action extends to an action, and this action is trivial on the boundary. So using this, Osawa proved that we have the following, that if what I take now the left times right action on the Stone-Check boundary of the group, we have a factor from this to a continuous map from this to two copies of the visual boundary, and now here I consider only the left action, and here also this action is topologically amenable for what I say, and so this action is topologically amenable. And this is something that is really reminiscent of hyperbolicity. If you take a group which is not hyperbolic, it's very difficult to have this situation. And actually, the situation for the examples which are known are basically groups that are hyperbolic or groups that are constructed from hyperbolic groups by taking some extension by amenable groups in some sense.
But wait, you haven't defined for us hyperbolic group yet, right?
For hyperbolic groups, it's true. The price is that you have to replace the visual boundary by the Gromov boundary. And this is again true.
No, I'm asking what is a hyperbolic group?
Why?
What is?
What is an hyperbolic group? Okay, so one has to define delta. First of all, take delta greater than 0.
Yeah.
Take the Kelly graph. Okay, I suppose that the group is finitely generated. So take the graph, the Kelly graph of this group that is constructed in the same way as the free group. But now in general, you see, since you can have some some group of finite order, you could have, this means that you can have some loop in this graph. But okay, you obtain a graph that is a metric space and whatever, and now I say the following, that this is delta hyperbolic, a group is delta hyperbolic if whenever you look at the Cayley graph, you have the following. Since we have notions of geodesics in this Cayley graph, we can do the following. We have the notion of triangles, and now the point is the following, that for every triangle constructed, take 3 points here, we take a choice of geodesics from these 3 points, and the point is that if I take this delta neighborhood of this geodesic and the delta neighborhood of the other geodesic contain the third geodesic. This is the notion of delta hyperbolicity.
I'm familiar with this, but under the name Gromov hyperbolicity, no? Isn't this?
I think Gromov gave this notion, yeah. And we say, so for example, the free group is zero hyperbolic, in the sense that it's delta hyperbolic for everything. In general, if you have a general delta, you say that your group is hyperbolic. So this is the notion.
So it is not amenable.
No. In general, no. But this condition works both for amenable and hyperbolic groups. So this led Osawa to the definition of what is called bi-exact group. And bi-exact group is exactly this notion, that the gamma times gamma acting on the Stonchek boundary of gamma is amenable. So it's a dynamical concept. His proof was, Osawa was interested in the following problem. That was a problem about operator algebra. He wanted to understand, there was a major problem at that time, to construct von Neumann algebras which are prime, which cannot be written as tensor products of von Neumann algebra. And there were very few examples. And in this approach, he could construct many new examples. How? Well, he proved that if you have bi-exactness, then you have another property called AO property. That is the fact that whenever you take now lambda times rho as a unitary group representation from gamma times gamma to what is called the Calkin algebra, so the bounded operators on the Hilbert space and show gamma over quotient by the compact operators, this is called the Calkin algebra. This is a temperate representation, so it factors through the reduced group system algebra. He proved that this implies this, and at the end this implies another property that is called von Neumann solidity. I don't give the notion here, but in particular this property implies that for every infinite subgroup, when you look at the centralizer of this subgroup inside the larger group, is amenable. And it's really a counterpart at the level of algebras of this problem.
In this definition of the Gromov hyperbolicity, what do you know about uniqueness of geodesics, or this is irrelevant?
You don't know. No.
They are not necessarily.
Whenever you choose, you have this.
So this is not a small triangle. It can be also like.
Yes. Whenever you choose a geodesic, it should hold. Yeah. So okay, my interest, motivated by what I told you before, the need or the desire to find equivalent characterization of certain properties. So my interest was to try to find whether some of these implications can be reversed.
So say again, what is bi-exact?
Bi-exactness is the following, that you have your group, now you have both a left action and a right action on your group. So you have an action of gamma times gamma, because they commute. And then you can extend this action to the Stonchek boundary, that is the biggest possible boundary. Now, bi-exactness is the fact that this action is topologically amenable, is is amenable in the sense that I define here. So what I wanted to understand is whether some of these errors can be reversed. And in particular, during the last 2 or 3 years, one of my interests was in understanding this part. Now, in order to understand this, what I did was the following. I tried to find a common framework for those 2 properties. And what happens is that we have a common framework, and the common framework is given by what I call the non-standard boundaries. So I will try to explain this. Yeah, I have to use some something a bit, but you can stop me and ask me. But so the definition is the following. So we start with omega, that is an ultrafilter over the natural numbers, free ultrafilter. So now I just use some operator algebras, but we can construct what is called the ultra product with respect to this ultrafilter. And this is just all the sequences in x, the x countable set, and gamma which acts by bijections on x. You see, this is a bit more general than the situation we have here, but the situation here is just a particular group that is gamma that's gamma, which acts on gamma. So this is just a more general situation of this. And we want to understand.
And the definition is Kaufmann operator? No, because you use measures here, but it is just action of the group of measures, and you don't use Kaufmann.
Of course, Koopman representations are the most important.
Yeah, but did you use it here in the definitions? No.
Which one here?
Anywhere.
Here there are no Koopman representations
So you
involved.
haven't used it?
No, but there will be very important.
Why I am asking, because when one has Klein group or Fuchsian group, then one considers product, and then one has good measure on the product on the boundary, which is a conformal measure.
Yes.
Which behaves very well.
Yeah.
If it doesn't, I'm sure that I understand what you are talking about, but I have some association with Fuchsian.
Yeah, you're right, and I think that this is actually a very important point, and
invariance then is up to some Jacobian.
yes, but I didn't go through the analysis of this, but yeah, this is important. Yeah, but anyway, Koopman representations will come briefly. So for now, I just take this situation that is just a generalization of the situation that we have there. And we want to understand really what is the relationship between amenability here and the fact that this representation on the Galkin algebra is temporary. So this is basically what we have there. The difference between AO property and bi-exactness is this is the question. So now I do this interlude. I take this particular space that is ultra product and is defined by all the sequences on L infinity of x, uniformly bounded sequences, quotient by a certain ideal that is exactly the ideal of sequences such that the norm of Fn goes to 0 with respect to the And then we also have an injection, a copy of an infinity of x. Just take functions and you put them diagonally. Constant, the sequence that is constant. And this is a gamma equivariant injection. So there is this fact in the theory of operator algebras that whenever you have a commutative sister algebra, this is the same as having a compact Hausdorff space, and the commutative sister algebra is the continuous function on this space, and this association is factorial.
As Gelfand, nein.
Exactly, exactly. So in particular, we have the converse of this situation at the level of spectra of these spaces. So we have the spectrum of this ultra product. This will subject in a gamma equivariant way on the spectrum of this, that is just the Stonechek compactification of x. And I define the non-standard boundary of x as the inverse image under this surjection of the Stonechek boundary. Now this is just a definition, it's a definition. And now what is the point of having this definition? Is that now I can translate everything in my problem about measurable dynamics on these particular extensions of the Stonechek boundary. So first of all, one thing that, this is maybe important to mention, that in general, we have the following, that if we have gamma acting on a compact Hausdorff space, if we ask whether this action is amenable, this is equivalent to the following. We should have two properties that are satisfied. One property is that for every quasi-invariant measure on this space, the associated Pugma representation is temperate. So we have automatically Pugma representations and quasi-invariant measures. And also that there is a particular very strange property that I don't understand very much, but is a bit reminiscent of the topology of the space, that is called pair-amenability by Claire and Antomaran de la Roche. It is the fact that we have a particular equivariant projection from this to an infinity. This is a strange property that, but okay, topological amenability is equivalent to the fact that whenever we have a quasi-invariant measure on this space, these two properties should be satisfied. Now, using this, it is possible. So you see, in this situation, we have something like this. We have this is the Stonechek boundary of this countable set. We have all this cloud of these very complicated spaces, which are these non-standard boundaries. Okay, and now what is topological amenability here? The point is that the action of gamma acting, we choose one of these particular extensions. We looked at this. This is topologically amenable if and only if the action of gamma on the Stonechek boundary is topologically amenable. So this is a very strange phenomenon. In general, this is not true. If you have amenability here, you obtain amenability on the extensions. But the contrary is very, very difficult to have. But in this case, it's true. So in particular, using this characterization, we see that bi-exactness, or the fact that the action on the Stonechek boundary of this set is topologically amenable, is equivalent to the fact that when I take, so for every of these spaces, I have this associated to it, this set of quasi-invariant measures, and the amenability of this is the same as the fact that whenever I pick any of these measures, mu, we have these two conditions. So pi mu temperate and peramenability. Okay. Now what is the content of the other condition of this AO property? Is the following. So I can construct for every ultrafilter on the natural numbers, I can construct particular sets of quasi-invariant measures which are Wixter dense, such that every measure in the smaller set is peramenable. Okay, this is one factor. And the other fact is the following, that if we take tau as a star topology, so a family of group representations, then the Kalkin representation, so the representation from gamma to the Kalkin algebra, is tau continuous if and only if for every mu in this other set, pi mu is tempered. So now we see really the difference between topological amenability of the action on the Stonechek boundary and the regularity of the Kalkin representation, and the difference is here. So topological amenability is the fact that all these quasi-invariant measures on this cloud of extensions satisfy these two properties, and the regularity of the Kalkin representation is the fact that I have a Wixter dense subset of measures in which that I can describe explicitly, in which these measures all give rise to tempered Koopman representations. So this is really the difference of these two properties put together in a common framework. Now, for the time being, I couldn't go forward, but okay, I'm working on this. And okay, so this was to state the fact that these two properties, bi-exactness and AO property, can be described in a common framework. That is measurable dynamics on some spaces that are very difficult, but okay, to understand. But this is the point. Now I want to. Okay, and also you see, if you are looking for the AO property, we also have another dense subset of probability measures, in which here we have both conditions. And peramenability. So the difference between bi-exactness and the AO property really lies in very strange measures that are in the closure of these subsets. Okay, now I found these results, and now together with Florin Radulescu, we were trying to understand what happens in some cases. You see, one of the drawbacks of this approach is that we can also define a quantitative version of AO property. Because here I have a characterization also whenever I take a C-star topology. So I recall you this is take a family of group representations, and I can construct a C-star algebra out of this family, and I ask whether this representation maybe it doesn't factor through the reduced group C-star algebra, but maybe factors through this other completion that I obtain. And maybe this could give you information about the group. And this is what we tried to do together with Florin Radulescu. So in order to describe this approach, I want to focus on a particular class of examples. And the class of examples are our favorite groups that are SL and Z. So let's see what happens for these groups in terms, I mean, at this level. So for n equal to, okay, one could say this is hyperbolic, and so we already know the result that this is bi-exact, and so I have for this. But I want to give an alternative proof of bi-exactness, because this will be useful for what I'm going to say. And this is it's inspired by an idea by Furstenberg when he was studying Poisson boundaries of groups. And the idea is really the following. Consider this map from gamma, and the range is 2 by 2 projective matrices over the real numbers. So what is this? Is you take 2 by 2 matrices, you remove 0, and you quotient by the action of the multiplicative reals, just by multiplication. And this map sends an element to the projective matrix gamma. And now you see, we want to see what happens when we extend this map to the Stone-Check boundary. Now this means if you have the range that is separable and so on, this means that what you want to understand is really if you have gamma n, a sequence of elements in this group, and suppose that this sequence goes to infinity. Now the argument by Furstenberg was the following. Look at the two columns of these matrices, call them Wn, Dn and Wn, for example. And so the fact, so this is Dn, this is Wn. The fact that the determinant is 1 is exactly the fact that the area of this figure is always 1. And so if these group elements go to infinity, we don't have many choices on these two column vectors. Either up to subsequences, either one of the two goes to infinity and the other remains bounded, or otherwise if they both go to infinity, the directions should converge in order to keep the determinant 1. What does it mean at the level of this map? It means that the range is given by projective matrices of rank 1. But what is a projective matrix of rank 1? Is just the data of the range and the kernel. So this is actually a copy of the real projective line times the real projective line. And the left action on this translates only on the movements of the range, and the right action only moves the kernel. And now the dynamics of SL2Z on this basis is well understood, and we know everything, and it's amenable. So in particular, we obtain that this product action is amenable, and we retrieve our bi-exactness. So okay, this was just another approach that, by the way, will be useful in a moment. Now we look at what happens if I take, let me erase. N that is greater or equal than 4. So we take SL and Z, we then greater or equal than 4. Well, in this case, you see, I say that the last of these properties implies that the centralizer of an infinite subgroup is always amenable. But in this case, we take SL and Z, we will have here on the top let's corner a copy of SL2Z, and here 1. But in this part, we certainly have elements of the centralizer of this group, and this will contain a copy of SL2Z, which is not amenable, since it contains a free group control generators. So in particular, for n greater or equal than 4, all these properties fail. Okay, what happens if I take n equal than 3? This is a major problem. We don't know. This is actually it's always the case that when you have rank 2, it's always the most intriguing phenomena that are appearing. And so together with Radulescu, we tried to understand what happens in this case using that approach and using the Diagonal-Fürstenberg. So now we repeat this approach. Now we modify a little bit that map in order to have more information. What we consider is the map from gamma to products of projective matrices and because we want to consider both gamma and gamma to the manifold. And this is related to the fact that otherwise we lose information about the Lyapunov exponents. But okay, we define this map, and now you see in this particular case, we were interested in this part. We wanted to understand this for the case of SL3Z. Now we go back to the case of SL2Z, just to make it clear. In that case, we have this particular space that is very well understood. The action of gamma times gamma is very well known. Now this is a quotient of a factor of the action of gamma times gamma on the stone-check boundary of the group in the case of SL2Z. So the approach, if you really look at this, is the following. We have some dynamical properties here, for example, topological amenability. We lift these properties to properties of this other space, and then we try to retrieve properties of the Galkin representation, of this representation. In order to deduce the Euro property, for example. Now we want to do the same, and now we can repeat the argument before. And so we take a 3 by 3 diverging sequence, a diverging sequence of 3 by 3 matrices in SL3Z. And now what is the point? Well, if we repeat the same argument, here we will have 3 vectors, and the fact that the determinant should be 1, it means that either they all converge to the same direction, or there is a plane, and the third one converges to this plane, up to some sequences. So what we obtain here, something similar, but it has 3 sections. In one section we obtain rank 1 times rank 1 matrices. In the case this diverging sequence, all the columns converge to the same direction. In another case we obtain rank 2 times rank 1, and in this other case rank 1 times rank 2. And then we want to use the same strategy to see if from dynamical considerations here we can lift dynamical considerations here and then obtain properties of this Galkin representation. So now in this case, this particular set is very well behaved. In particular, the action is amenable. And okay, so we restrict to the other 2 sets. It's not difficult to see that the dynamics on the rank 2 times rank 1 is the same as the dynamic on rank 1 times rank 2 in every possible sense. And so we restrict to just one of these. of Abels, Margulis, Furstenberg, Seufer, probably someone else. They studied, I think it was Furstenberg who introduced the notion of quasi-projective matter. It was a generalization of projective matter. And in the language of Abels, Margulis, and Seufer, these are called proximal linear maps. And they really study proximality behavior of certain actions. And our lemma was inspired by this. And it's the following. Suppose now we have a sequence, so we are in SL3Z times SL3Z, acting on this particular set of projective matrices, or product of projective matrices, and suppose that both these go to infinity, both the length size, this come from the left action, this from the right action. So we are sure that up to a subsequence, there exists some sets C1 plus minus Ck, and these are in some sense lower dimensional varieties. With the following property, such that for every y in this space of projective matrices, outside the union I from 1 to k of Ck plus, the limit of gamma n eta n applied to y exists, so there exists, and this belongs to the union I from 1 to k of Ck minus. So what does it mean? It means the following, that given this divergent sequence, we have some very thin sets. This is Ck, Ci plus, and we have similar sets on this other side, Ci minus, such that whenever I take the point here and I move with this divergent sequence, I will go into this lower dimensional sets.
Repelling, attracting.
Sorry?
Repelling, attracting.
Yes, yes, we have this sort of behavior, exactly. Except of having one point, we have these lower dimensional varieties, exactly. And so this is actually a useful dynamical property. And using this, so now the approach here was to lift property from here to property from here, and deduce properties of this Calpi representation. And then here, if you look at the theorem that I stated before about regularity of the Calpi representation, what we should do is the following. So we have the dynamic here, we lift to dynamic on the Stone-Check boundary, and this is again not enough. We have to lift to dynamic on every non-standard boundary, and look there, and maybe deduce by means of the theorem that I stated before, properties of the Calpi representation. So the theorem that we proved in this case is the following. That now take mu, so what is important in the study of the Calpi representation were these particular measures on these extensions of the Stone-Check boundary. So take one mu, a probability measure of one of these non-standard boundaries, that is gamma times gamma quasi-invariant. Now I can decompose this measure in the sum, the orthogonal sum of two measures. One, so mu1 measure supported on orbits of this. CR. And the other one, which annihilates. So, annihilates this particular set. So, from the dynamical considerations that we had, we see that if a quasi-invariant measure gives measure 0 to all these sets, it means exactly that when we look at the Kubma representation, the matrix coefficients will go to 0. So, by what I said, we have that whenever gamma n at n go to infinity in both directions, we take this particular measure, we take pi mu 2, the Kubma representation of this sequence, we apply to an element in L2 of this, and this will go to 0. So in particular, these Kubma representations belong to a particular family of unitary group representation. And we call the family of group representations which satisfy this property. We call this family tau. Actually, we call it C0 prime. It's not exactly, the matrix coefficients are not in C0, but it's a slightly larger idea because we have to assume that both go to infinity. So in this case, such that pi mu 2 is C0 prime continuous, and also the other important result that is very technical and very reminiscent of the fact that we are in range 2. It's very important. The fact is that pi mu 1 is tempered. So mixing, so using this mixed with what I told you before, we obtain the following. In particular, the unitary group representation from gamma times gamma. Gamma now is SL3Z to the Kalkin algebra is C0 prime continuous. So it factors through the completion of the group system algebra in which we take the representations which satisfy this condition. And this is not true for SL and Z if n is greater or equal than 5. So actually this, we couldn't prove the AO property, but we found a property associated to this particular setting, to the Kalkin representation, which permits us to distinguish SL3Z from SL and Z with n greater or equal than 5.
Is 4?
4, I don't know. I think so, but yeah, it's probably the case also for 4, but I have to think about it. I think so. We are sure for LS and Z, then greater or equal than 5, and okay, so this was basically what I wanted to talk about. And now, what I think is actually that this Kalkin representation can distinguish all the SL and Z, and I think this is true, but it requires much work. Already this result was 1 year of hard work, but okay, so there are some rigidity properties that can be, I think that the Kalkin representation contains much more than just this, but okay, for the moment, this is what we have.
What would you call mixing?
Well, mixing, because you see, is this, that or a value. This means that the matrix coefficients are not exactly C0. So mixing, I mean that the matrix coefficients will be C0. That if you take a divergent sequence in the group, you take a quasi-infinite measure and the function, then this function, so for me mixing the two goes to zero. That the scalar product between an L2 function and the translate of this function by the group elements should go to zero. So in my case, it's not exactly like this because we require that the two components both go to infinity. So it's a bit bigger. And actually, okay, it is possible that it's actually zero, but it's related to other problems.
Question. So I guess the natural question is for which other groups you think we could apply this outside?
Well, what I think is that okay, we did only the case for SL3. This is, but if you look at the what are really the ingredients that we need in order to do this, is all the structure of these Borel subgroups, parabolic subgroups, and so on. And then we have to use some difficult operator algebra technique in order to find these results. But at the end, the ingredients are really this. So I think that this can be applied to, for example, lattices in semi-simple groups. This is what I think. But okay, first of all, we should look at the examples SL and Z with greater or equal than 3. And already there it's a bit messy, but at the end the information is all about the position of parabolic subgroups that we need. But we need to understand how to translate it. And today, I think that these two are equivalent, but maybe tomorrow we'll have another, every day I have a different feeling. And there is also something more I want to say, that in the first part I was concerned with the slightly more general situation in which we have the group gamma acting on a countable set, and to study temperateness of the Galki representation versus topological amenability of the action on the Stonechet boundary. Now this is, if one can prove that they're equivalent, that temperate of this representation is equivalent to topological amenability of that, it means that one has a tool in order to prove exactness of certain groups. For example, I would like to apply it to the Thomson group, because the Thomson group almost acts on a grid. And it's a major problem whether the Thomson group is amenable, but it's unknown if it's exact, that is much weaker. And this could be some information in that direction. And for other groups, I think that...
But wait, so if it's not exact, then you solve the problem?
Exactly. If it's not exact, it's not amenable. Yeah. But everyone thinks it's amenable.
Okay.
But yeah. By the way, yeah, what I think is that the nice drawback, okay, let's put it like this. We had a very difficult problem. We translated it in a problem that is maybe much more difficult, but at least in this different approach, we have measurable dynamics on some spaces that are very difficult to study. But we can use, for example, in this work, we use the properties of the measurable dynamics. So you can take factors, and you can see at the topology. For example, in a recent paper that I wrote, I used the particular properties of the topology on the spaces in order to answer a question by Anantara Mandela Roche on linear amenability. So you have some other tools that you can use here. And I think that there should be a
Okay. So if no more questions, let's thank the speaker again.